Okay, recording has started. Okay, so let's begin. So this just again, this is PYQ session of week 1 and 2. Okay, so this is question number 1 right here. Okay, do you guys want me to erase all this and start from the beginning, or is it okay if I just explain this to you guys? So we were able to do, I guess, 4 or 5 questions. After that, we have 20 more to go. So do you guys want me to erase this and start from the beginning, or can I just explain like this? Guys, response would be appreciated.
Sir, you can just
Okay.
explain like this.
Okay, thanks. So in the first question, we are given x vector and the line passing through the origin represented by vector w. So we are given data point which is x and we are w, okay, which is representative for the line. Find the length of projection of x onto the line defined by w. So we just have to take dot product of this, right? So the projection vector is what? X transpose w into w divided by norm of w, norm square of w. Okay, so we want to find norm of this thing right here. So just take norm of this. So this quantity is a scalar, this quantity is a scalar. This is the only vector we have here. Okay, so if you take norm square of this, you will get norm square of w in the numerator, and in the denominator you also have norm square of w. Okay, so these both get cancelled and you're left with x transpose w. So here x transpose w is what? It is equal to 7, and this is norm square of length of projection. Okay, so they are asking us for norm, so simply take root of this. Yeah, so is this clear? This was pretty straightforward question. Is there any problem in this? Yes, no? Guys, I would appreciate if you guys respond. Okay, respond. Otherwise, uh, I won't be able to understand the flow of class. Firstly, am I audible here? No, length of w is not 1 here. So the w vector is 1, 1. So its norm is equal to 2. Norm square is equal to 2. Is this question clear to you all? Hello? At least tell me, am I audible or not? Okay,
You're audible.
let's continue. Okay, thanks. Let's continue. So in the next question, we have to calculate the magnitude of reconstruction error after projecting x onto the line defined by w. So this is also straightforward, right? So we know that reconstruction error is what? Xi minus xi transpose w into w, and if norm of w is not equal to 1, we'll divide by norm square of w, right? Okay, so we'll just use this here, and here your x vector is this, and your x transpose w is equal to 7, and norm square of w is equal to 2. So that's why 7 by 2 here, and this 1 1 is your w vector. Just simplify this, and this is the reconstruction error vector you get. Now if you take norm of this, you will get 1 by root 2. Is this clear? Hello, is this clear, guys? Thumbs up, thumbs down, yes, no? Guys, I'm waiting for response from your end. What is this? Am I audible? Hello. Okay, let's continue. Yeah, I would really appreciate if you guys interact. Okay. So in the next question, okay, we have to find which of these expressions is reconstruction error for data set of n data points with with respect to line passing through the origin. Okay, and the line is represented by w vector, which has norm equal to 1. So this is the average reconstruction error, right? This is the average error. So it's simply 1 by n summation I from 1 to n, norm of xi minus xi transpose w into w, and we are not dividing by norm square of w here because its norm is equal to 1. Okay. So this is first expression. and this is the same as first option. Okay, and now if we use the formula, so we know x transpose x is, so norm square of x is equal to x transpose x. So we are applying the same thing here. So this becomes equal to this expression, and this is the second expression we have here. Okay, and if we further simplify it, okay, if you distribute the transpose here and multiply everything, so in the end we get this expression, if you guys remember from the theory part. Okay, so this is another expression which can be given in options, but it is not given. There is something similar here, okay, but it is not the same thing. Here you don't have a minus here. If we have minus here, this option is also correct. Okay, so is this part clear? Is this clear to you all? Hello.
Yes,
Okay,
yes.
let's continue. Let's continue. Let's quickly finish the easy questions. Okay. Uh, and in the next question, we are given data set D, and here we have to find, using the normal PCA, we have to find along the first principal component what is the variance. So the good thing about this data set is that all the points here, I mean all the vectors here, lie on a straight line passing through origin. So if that's the case, the PC1 will be the line itself, and it will capture the entire variance of the data set, right? Correct?
Yes. Projected will be the same data points.
Yes. So after the first round, the error will be zero. So the line, the W vector, the W1 will capture all the variance you have. So is that clear? So yeah, one thing here, my bad. So here the variance will not be one here, because here you have to find the variance of the data set here. Okay, so simply apply this formula. This is actually variance, right? You just have to apply the formula here and find the variance. So could you guys do the simplification for this? So therefore, for finding the variance, just find the variance of data set. Yes. So is this clear? What's the approach for this question? Hello.
Yes, yes, yes. It's clear.
Okay. Okay, let's continue. Okay. Now we just have one more question left, and after that we'll start with all the new questions. Okay. So here in this question we are given covariance matrix and W1, W2. So we have to find the variance of the data set along the first principal component. Okay. So along the first principal component we want to find what is the variance. So what is first principal component? It is the eigenvalue, right? It is the eigenvalue corresponding to the largest eigenvector. Okay. So what is the variance along that direction? It is the eigenvalue, right? So here we just have to find the eigenvalue of covariance matrix. This is the covariance matrix, and where eigenvector is this. So using the eigen equation, which is CW1 equal to lambda 1 W1, this is the eigen equation. Here you simply put the value of C and W1 and simplify. So I'm just taking out the constant here from the W1 and writing it here. This is the constant, this is your W, and this is this is your C, and this is W1. These both combined are W1. So if you multiply this with this, you will get 3, and same for this. Okay, now this is the simplified version. So now here you have to break this into two parts. One is your W1 and the other will be constant. So for this we'll take out 3 common. Okay, so this here we have 3, and this right here you have W1. So this 3 is your lambda 1, and this 3 is your what? It is the variance along PC1. Is that clear? Hello.
Yeah, that's clear actually. C W1 equal to lambda 1 W1, right?
Correct. So this right here, we know this is the eigen equation. We are just using the left hand side of this, right? And we are simplifying it to the right hand side to get the lambda one. Is that clear? Is there any question in chat? Let me see. What is going on? Okay. Okay, so let me tell you, this is MLT series by Saranda House. And in this session, we are taking week 1 to previous year questions. Yeah. So is this question clear to you all? Okay, I hope this is clear. Let's continue our discussion and let's move to new questions. Okay. Okay. This is interesting one. So here, so in the next part of this question, what we have to do, we have to find the variance of the data set along x-axis. Yeah, any idea for this? How we will do this? Anyone? Any suggestions for this question?
So the W1 will be 1, 0.
Correct, absolutely correct. That's the entire thing. Okay, so let's do this last second part. Okay, so finding variance along x-axis. Okay, so we all know that from the theory that what is the optimization problem in our hand? It is W transpose CW, right? And what is the solution for this? I mean, this is the optimization problem. That's correct. What is this equal to? So this is equal to your lambda, right? Is this clear? Do you guys remember this? Hello?
Yeah, this formula we can use for the previous one also, right?
Yes, I mean
Uh,
it's actually coming from the same thing, right? It's actually coming from the same
yeah,
thing.
this CW1 lambda 1, yeah, the same. Yeah, we can use this and directly find the lambda right here
Yeah,
in the
both are the
given sum.
essentially both are the same. So right here, and we know that this right here, this quantity is nothing. I mean, we know that lambda is variance, but you can also expand this, right? You can simplify it, and this is equal to what? 1 by n summation I from 1 to n. Then you have xi transpose w whole square. And why is that? Because data is centered. We assume that data is centered, so the mean will be equal to 0. So that's why you are not subtracting mean from this. So, and this is what? This is your variance. This is your variance. So here, yeah, sure, we'll share the slides or notes. So here we know that this lambda is, so lambda is variance along W. So if you want to find, so for finding the variance along x-axis, take W is equal to basis of the x-axis direction, that is 1 0. So this is simple. So now variance along x I am representing by this. This is equal to what? W transpose C W. And what is your W here? It is equal to 1 0. And what is your C here? Anybody remember? 2 1 1 2, I guess. Let me check this. 2 1 1 2, correct. And again W. So just simplify it. So let's simplify this part first. So this will be equal to vector 1 0 transpose of this vector multiplied with, and from here you will get 2, and here you will get 1. Yes. So this is dot product of the two. So this is equal to 2. Yes. So this is your answer. So is this clear? Hello? Hello, is this clear?
Yes, yes, yes.
Yeah. So guys, uh, given any direction, can you guys given any direction? Okay. Given any direction and given covariance matrix, can you guys now find the variance along that direction?
Yeah, we need to find the unit vector along that direction and then use this W transpose CW, right?
Yeah, absolutely correct. Yes. So let's continue our discussion. And this is the next question you have. So in this question, we have to find the coordinates of the point 2, 2 in new coordinate system formed by principal components. So if we move to coordinate system of W1, W2, what is the new coordinate representing this point right here? Yes. So any idea how to approach this question? Anyone? Okay, I have a slide for this. Let me show you guys. Just a second.
Sorry for interrupt, but I am an ES student. Does I need to learn this?
No, I mean, if you want, you can. But I don't think you guys have MLT in ES, right? So this is just for MLT students or people who are curious who want to learn MLT. This series is for them only.
Okay, I want curious for this.
Yes, sir. So this is the idea right here. Okay. So we have E1 to E1, EM. These represent your W's here. Okay. You have W's here. Then you have data. Okay. These are original coordinates. Then we centered the data. Okay, we'll assume that data is already centered, and after that we are given covariance matrix. Okay, and now to find the uh, new coordinate, we have to use this. So we'll just remove these. Okay, let me modify it. Okay, so for the approach for it is that, let's say this right here, x1, x2. So this is transformed data point, you can say. Okay. So now uh, this is the covariance matrix. Okay. Sorry, these are W1, W2. They are important to you. So W1, W2. This we have here. Okay. So now what we will do for the, so now this W1 represents your, this becomes your x coordinate, right? And W2 becomes your y coordinate, correct? Is that clear? So now what we will do, we will take dot product of this W1 with the data point to get the x coordinate in new coordinate system, and to get the y coordinate of data point in new coordinate system, we will take dot product of W2 with the data point. So this right here is equal to x, or I can say, okay, let's represent the original vector. Okay, let x is equal to this 2 2. So the vector is equal to, so the x coordinate for this is x transpose W1, and the y coordinate is x transpose W2. Is this clear? Because we are projecting the data point in new system, right? New coordinate system. You have a data point.
I'm not
You get,
getting that actually. The projection after taking the projection, we will be seeing this X transpose W1 into W1 plus X transpose W2 into W2, right? That is how we will be calculating the
Okay,
projected vector, right?
that becomes a vector, right? But you are just concerned with the length of it. So, okay, I get your point right here. You are saying it should be X transpose W1 into W1, right? Is this your what you are saying?
Yeah, yes, and then plus X transpose W2 uh, into W2. That's how we will be seeing the new projected vector, right?
Okay, wait a second. Could you please repeat? Okay, maybe yes. There is some slight modification here. Just a second.
But
Mm,
answer what you are showing is correct. Your method is correct actually, but I'm having a confusion here. Um,
mhm.
in my
So
method,
that
I'm
gives you
getting a
the
different.
okay. Okay, you are saying this. Use this plus X transpose W2 into W2. Use this, right?
Yeah, yeah, I'm saying
So
this
this
one.
will give you the original data point, right? This is if you if you have if
Okay,
you have data
it is
set such
giving the
that
original data point.
this will give you original data point. What's
Yes,
the
but we
we
want only that projections. I'm not getting this coordinate.
okay let me explain you this. Okay, first of all, let's discuss why this right here is not correct, because we know that data points are what? Data points are linear combination of w's, correct? So this
Yes,
right here is used to go uh, from the w's. This is how you go back to the original data point, correct? Do you remember that?
yes, yes.
Okay, so this is clear. Okay, this part is clear why this is not correct. Now, coming to why this is the right approach. Okay, let's focus on this. Let's focus on X transpose W1 into W1. So, this right here is projecting your data point onto W1, okay, and then multiplying it with W1. So, that gives you the proxy vector, or you can say the projected vector, correct?
Yes,
Okay, that's clear. But we are only concerned with the length of it, right? We are just so W has length 1. W1 has length 1. All the W's we take such that the norm is equal to 1. Even here in this example, the norm is equal to 1. So the length of this will be equal to what? X transpose W1 only, correct?
yeah,
So now just imagine that this is your XY plane, original coordinate system, and this is PC1, this is PC2. So this is the point. You are taking the projection, okay, on this PC1. So the vector you will get is this, correct? This is the length of the vector. Is that clear? Okay. Or do you want me to draw a
yeah,
bigger
it's
diagram?
okay. This is okay.
Okay, so let me zoom. Okay. So this is the length along that PC, and on projecting on the PC2, this is the vector you get. Okay, these are the two vectors. So if you're making this axis your x-axis and this axis your y-axis, then only the length of this, so the length of this will be what? X component, and the length of this will be what?
Oh,
Y component.
yeah, yeah, yeah. Got it, got it. Thank you.
Yeah, thanks. Asking questions helps others also. Okay. Yeah. So thanks for asking the question. Okay, so let's continue our discussion. Or let me bring this to the center. Okay. Yes. So let's continue. So now what is X transpose W1? Okay, so X transpose W1. X is where is X? Okay, W22 is your X. And W1, if you take a dot product, so this will be 2, 2. Sorry, 2 plus 2, 4. Okay, let me do that here. So your W1 is what? W1 is 1 by root 2 1. Okay, on taking dot product with 2 2, so this will be equal to what? 1 by root 2 into 2 plus 1 by root 2 into 2. Okay, so basically this is equal to, so you get root 2. Okay, and here also you get root 2, so this is equal to 2 root 2. Okay, so this is 2 root 2 here, and x transpose w2 will be 0. And why is that? Because on taking dot product of vector 2 2 with this, so what you will get here, so this will be equal to, okay, we are taking dot product with root 2, so this will be 1 by root 2 into 2 minus 1 by root 2 into 2, so this is equal to 0, right? Correct. So the y component will be 0. So this is now your vector in new coordinate system. So is this clear?
Yes.
Is this clear to
Yes.
you all? Hello. Okay, let's continue our discussion and let's move to the next question. Any questions so far from anyone? Any doubt? Anyone? Okay, let's continue. So the next question, this is your next question. So standard PCA has been performed on a centered data set in R3. The first two principal components are given by W1, W2. Okay, consider the data point in the data set. This is the data point. Okay, AB is the representation of this point in the coordinate system formed by two principal components given below. Okay, the first principal component and the second principal component. So what we have to do here, we have to find the values of A and B. Basically, we have to find transformed data point in the new coordinate system. So do you guys want to give it a try?
Is this the same like the previous
Yeah.
question, right?
Yes,
So
correct.
we need to take like x transpose W1 will give me the A value, and then x transpose W2 will give a B value.
Correct. Correct. Okay, let's finish it. Okay, let me finish it. Or do you guys want to try this and find the answer? Whatever you guys say. So your AB here will be equal to, let this is your x. Let x is equal to 2 1 minus 1. Okay, so A will be equal to x transpose W1 and B will be equal to x transpose W2. So what is x transpose W1? Anyone? So x transpose W1 is equal to
2 by
1
root
by
3.
2 by root 3.
2 by, okay, thanks. 2 by root 3. And what is this x transpose W2?
1 by root 2.
1 by root 2. Thank you. So now this is your answer. Okay, let's go ahead. Let's move to the next question. Okay. So the eigenvalue of covariance matrix of a centered data set in R5 are these. Standard PCA is performed on this data set. What is the variance captured by top two principal component expressed in percentage? Okay, expressed in percentage of total variance. But this is also very simple, right? So we know that eigenvalues are nothing but variance of the data set along the direction of their corresponding eigenvectors. Eigenvectors are W's. So the total variance is equal to what? Total variance is equal to sum of this. That is, it is equal to 50. And top two are capturing how much? 40. So, okay. So total variance. Thirty plus 10. Do you guys want me to write the reasoning that eigenvalues represent the variance and all that? Or is it fine?
That's okay.
Okay, so this is equal to 50. Variance captured by top 2 is equal to what? It is equal to 40. So in percentage, so the answer
80.
is 80%. Okay, thanks. Yeah, this is also simple. Okay, let's move ahead. Okay, is there any doubt? Anyone?
So if suppose we have the say here itself the second and third are same, right? Can we say that as the top three because both are having the same values 10 10.
Correct. Yeah, that can happen, right? What's could you repeat your doubt again?
My doubt is can we say that the if suppose the question is like that
Mm-hmm.
by top three principal components, then
Mm-hmm.
can we add that last 10 also
Yes,
because both the
yes, yes.
values are same, right? 10 and 10
Like
are
if
same.
yes, both of them are capturing same
So
amount of
it would be
variances.
100%. 30
Yes,
plus
yes,
10 plus 10 divided by.
yes. Correct. Okay, let's move ahead. Okay, so in this question, consider a data set of 50 points, all of which lie in R5. The eigenvalues of the covariance matrix are given below. If we run PC algorithm on this data set and return the top k principal components, what is the good choice of k? Okay. So guys, if you guys remember when we were discussing how to find the value of k, nobody will tell you the value of k, right? So the thumb rule for that is whatever k you are choosing, okay, the sum of the variance captured by them in percentage should be greater than equal to 95%. Okay, so summation. So here the summation I from 1 to k of lambdas divided by all the lambdas, sum of all the lambdas. So we have 1 2 3 4 5. Okay, this multiplied with 100, this will be okay. So this quantity must be greater than equal to 0.95. So you just have to take values of k, okay? Take first two and check if this condition is satisfied or not. Take first three and check if this condition is satisfied or not. This way you will find the value of k. Is that clear? Yeah. Is this clear to you all? Hello?
Yes, it's clear.
Okay, let's move ahead. So now let's pick first two, okay? So the first two are what? Okay, so take k equal to 2 and check. Okay, so now here it is 1.7 plus 1.4. Wait a second, my pen. Let me move this up. Okay, so this is equal to, okay, just what is it? 1.7 plus 1.4 divided by the sum of all. Okay, so sorry, 1.7 plus 1.4 plus 0.25 plus 0.2 plus 0.05. Yeah, could you guys tell me what is this sum?
So 3.585.
Okay, sum of all is 3.58.
Yes.
Okay, so 3.58. And what is sum of the top two?
3.1.
3.1. Okay, so here 3.1 divided by 3.58. So this is equal
86.
to, yes, 0.86. Okay, so we'll take k equal to 3 and check. Okay, that I guess that will be correct. So take k equal to 3 and check. Okay, so I'll simply copy this. And we'll add one more, that is 0.25. Then what's the value? 3.1 plus 0.25. So this is 3.35 and divided by 3.58.
93.57%.
Correct. So okay, still this is not equal to, greater than equal to, okay, 95. So we have to take one more, so that will be correct. Okay, so we'll take k equal to 4 and check. Okay, so again, so we'll add, what's the other thing? 0.25, then 0.2. Yeah, so this must be greater than equal to 0.95, I believe.
It's 99.96.
So this is equal to 3.3 divided by 3.58. Yes, wait a second. 3.3 this is, and this is divided by 3. Still, it is not greater than 95. It is 92, right?
So it's 3.55 in the
Okay,
numerator.
okay, sorry. 3.55. 55 divided by 3.58. Yes, now this is correct. 3.55 divided by 3.58. Yes, so this is 99%. Yes, so answer is k equal to 4. So is this clear? Hello. Is this clear to you all? Hello.
Yes, yes, sir.
Okay, let's continue and let's move to the next question. So suppose a data set lies in R4 and under PCA principal component analysis, after being centered, okay, the resulting first and second principal components are given to you, and you have to find which can be the third principal component here. Okay, so here we'll use that here we'll use the information that whatever is the third principal component, that will be orthogonal to first and second principal components, right?
Yes, sir.
Correct. Yeah, so could you guys check and tell me which vector here is orthogonal to PC1, PC2?
The
Take the
last
dot
one,
product, put it equal to 0. Okay, the last one.
the fourth
So
one,
let's
fourth
check.
option.
Okay, let's check that. So W1. Okay, so this is W1. This is, let's say, W2, and this is your X. So your X transpose W1, let's check. So here you have 1. So this first is 0. Then here you have -1. So this is -1. Then you have 0. Then you have 1. Okay, yeah, this is 0. This is 0. and X transpose W2. So the first value will be 0, second will be 0 here. Okay, then you have 1 and then you have -1 here. So this is also 0. So this is correct. W3 will be perpendicular to W2 and W1. This is what you are using here simply. Yeah. So any problem here in this question? Hello. Okay, let's continue our discussion and let's move to the next question. Yeah, this is the same thing, right?
I think we did it
So here we are
already.
given W1, W2. We are given the data
I think
point
we did
and we
it
have to
already.
yes, we have done the similar question already. Okay, so let's leave this. You guys can try this one. I'm leaving this. So let's move to the next question. Okay, this one we already did, right? Okay, I guess I have repeated two questions. Okay, leave this and let's move. Wait a second. This is also done. Sorry. Yeah, let's move to this question. So, which of the following statements are true regarding applying standard PCA on centered data? The first option is the variance of data set along the first principal component is maximum. Okay, that's true. The first option is correct. The eigenvector are always orthogonal to each other in PCA. That's also correct. The first principal component is the eigenvector corresponding to the largest eigenvalue of covariance matrix. That is also correct. Again, in the last option, we are given smallest eigenvalue. So that's not correct. Yeah, this is also straightforward. Is it clear? Hello?
Yes, it's by definition.
Yes. Okay. In the next question, given n data points in d-dimensional space with non-linear relationship, we apply kernel PCA to reduce the dimensionality and select the first k principal components. Is it possible for k to be larger than d? Yes or no? Anyone? With the explanation and answer for this?
Yeah, actually, that for two dimension, then we can go up to six. Right?
Yes, correct. Because the data set is such that it is in non-linear fashion, right? The relationship, the underlying relationship of the data points, they are non-linear. Okay, so they do not lie in linear subspace. So to capture non-linear relationship, what we do, we transform our data point to higher dimension such that in higher dimension it is in some linear subspace. Okay, so let's say your data is in R2, you move it to R6. Okay, so now your data is in R6. So after applying PC on this data, you can move to R3. So uh, originally you had data in R2, and in the end you are moving to R3. So it may not look like reducing the dimension, but actually it is, because the linear relationship that can be captured only in R6. Correct. So and from there we are reducing. So is this idea clear? Is it clear to you all? Is it clear? Hello, anyone? Is this clear? Okay, is my screen not visible?
Yes, it's clear actually.
Okay, let's move ahead. Okay, now in the next question, we are given kernel functions and we have to check if they are valid or not. So what's the approach for this? Anyone? Any suggestions how to approach this problem?
We use some Mercer's theorem.
And what's that?
We check the commutative property of the kernels.
Okay, so there are two necessary conditions. Okay, the first is the kernel function must be symmetric, correct? And the other condition is that kernel function must be uh, semi-definite, positive semi-definite, right? So these are the two conditions. But we can directly check if the function is symmetric or not by replacing by interchanging the uh, x1 with y1 and x2 with y2. That can be done. But to check if this is positive semi-definite or not, we will need data. We'll need the data set, right? But that's not given. Okay, you may have, I guess, you have other methods, but that will, I guess, involve integration and all that. So there is another easy way of doing this. Do you guys have any idea? We have done that already in sessions and in lectures also. Uh, Professor has done it. Okay. So what are we actually doing with kernel function? So with kernel function, we are transforming data to higher dimension. We are transforming it to higher dimension and then we are taking dot product, correct? So if you give two vectors to kernel function, what it will do, it will move them to higher dimension where they have linear relationship, okay? And then it takes dot product of the two. So if this function, if we can break it into two vectors, okay, if this is equal to dot product of two vectors, then this is a valid kernel function, right? Is that clear? Hello, is this clear? Okay, let me show you guys this from the lecture notes. Okay. Okay, this right here, let's see. So this is a valid kernel function. Okay, we are given that this is a valid kernel function. So on simplifying this, this is the result we get. And this can be broken in dot product of two vectors. So is this idea clear? Hello? Hello?
Yeah, this is
Yes.
clear, but how to break that uh, function into two functions?
Okay, let's look at that. Let's look at that. Okay, just a second. Okay. Screen got stuck. Okay, now the question is how do we break the function into two vectors? So let's check the first one. So k1 xy is equal to x1 y1 plus x2 y2 plus x1 plus x2 into y1 plus y2. So if you look at carefully, this is equal to x1 x2 x1 plus x2 transpose of this vector into y1 y2 and y1 plus y2. So this is dot product of these two vectors, correct? Is this clear? Hello, is my screen visible or not?
Yes, but how you did this split?
Okay, just look at the function, right? Okay, this is x term, this is x term, and this is x term here, and we are multiplying them with y terms, correct? So make a vector of x components and make a vector of y components. If you take the dot product, you will get to this. Is
So
it
can we say like this? So each component has to be symmetrical with respect to x and y. Then it can be represented as
okay? I mean, I have to verify that with other examples as well. You can verify that yourself, okay? If you have other examples, okay? In next question also we have similar questions, so we'll check there also. That's true. Because if you'll just check the symmetricity, if that so by the theorem you have two conditions, right? The function must be symmetric and it must be positive semi-definite. So just by this symmetric property, you cannot state that it is valid. It would be, to be on safer side, you can just try splitting the function into vectors.
no, that's what I'm saying. Each of them has to be symmetric, right? Each term. Is there any shortcut to do this? That's all.
uh, Not in my knowledge. This is very easy, right? Just look at the function. This is a simple function.
Yeah. Okay. Got it.
Okay, whereas if you check for x2 k2, you can, so this you can make part of x vector, this x vector, and but here the problem is, how will you split this, and how will you split this? Okay, this you can split into root 2 into root 2, sorry, root 3 into root 3, but this is not symmetry, right? I mean, sorry, my bad. This is not product of x and y component. This can't be factorized into product of x component and y component. So that's why this cannot be represented in this way. This cannot be expressed as dot product of two vectors. So is this clear? So
Yes.
In the same example,
yes,
can you make that term as x1 square into y2 square?
that will work, because that can be broken into product of uh, x component and y component. So in some, I mean, a shortcut is, you can say, if function is such that each term of the function can be factorized into product of x term and y term, then that can be that you can split in two vectors.
Yeah. Okay.
This we cannot. Okay, so is this question clear to you all?
So
Yes.
instead of plus sign, what if you had a minus sign? X1 square minus y1 square. Uh, uh, it in that case wouldn't be a proper kernel, is it?
In that case, okay, if you have x1 square minus y2 square, okay, you
Yes.
can write this as x1, sorry, x1 plus y2 into x1 minus y2, correct, using the formula. But still, this cannot be factorized into product of x term and y term. This is, I mean, if you have only x terms here and y terms here, in that case you can factorize this into vectors, right?
So the
Here
two
you can,
vector should so two vectors should be split apart into solely x vector and y vector.
yes, correct. So the factors of each term, they should be one. If you have, let's say, two factors, so one should be completely made from x terms and one should be made completely from y terms.
Right, right. Thank you, sir.
Okay, thank you. Okay, so if, okay, let's move to the next question. Yes, this question. Here also we have to check if the kernel function is valid or not. So we are given that, okay, this entire thing is a kernel function. This part of this is a valid kernel function. This portion is a valid kernel function. We have to check whether this entire function is a valid kernel function or not. So how will you approach this? That's the question. Anyone?
Here you need to use that symmetricity property, right?
Correct, correct. So, if you want to check if a kernel is valid or not, you will use the approach of factorizing the function into dot product of x vector and y vector. If you have to show that they are not valid, you can use the symmetric property. Okay, the function is not symmetric, it means it is not a kernel. So here clearly this is not symmetric, right? Because this sine of x1 is, this is not always equal to cos of x2. Is this always true? No, right? This is not always true. I mean, you can check this mathematically as well. So, okay, how will you check this? So first of all, tell me, is this clear or not? Is it clear why we are concluding that they will not be equal always?
No, you could write like this, no? Sine of x1 is not equal to cos of x1, right?
You
Cos
can
of
write this. This is
x2.
all. I mean, for a particular value of x1, x2, they will be equal. In a case they will be equal, but always they are not equal. So if you remember the graph of sine and cos, you can validate it from there as well. The graph of sine is somewhat like, okay, so sine is like this, okay, like this. Sine is like this, and this is a slice of the graph, and cos starts from here, right? Like this is like this. If you take this slice, correct? You guys remember
Yes, correct.
this?
Yeah.
Okay. So clearly from the graph also, they are not equal. And there is another method of showing this. So if you guys remember a few formulas from trigonometry, uh, we'll use that here. Okay. So, okay. So we want to check if they are symmetric or not. So the only part is this we have to check sine x1 cos x2, because this kernel function inside it, this is a valid one, so we have to just check this. Okay, so let's assume that they are equal. Okay, so let's say, so let sine of x1 cos of x2 is equal to sine of x2 into cos of x1. Let's say that. Okay, let this is true. So this implies that this sine of x1 into cos of x2 minus sine of x2 into cos of x1 is equal to 0. So do you guys remember any formula from this?
Sin A plus sin A minus B.
Correct. Sine of a minus b. So this is equal to, using the formula, this is equal to sine of x1 minus x2. So this is equal to 0. But this is not always true, right? This right here is not always true. Correct? Is this clear?
Yes, sir.
This is not true always. Yes, so this is another way of showing this. Okay, so is this question clear to you all?
Yes, sir.
Let's go ahead. Let's move ahead. And this is the next question right here. Okay. So in this question, we are given kernel function. Okay. And we have to find the mapping. So how we will do this? What will be your approach? Anyone? We just discussed about it right few moments ago when I opened the slides of previous lecture. Okay, let's go there. Okay, let's look at that again. This is week 1, my bad. Week 2. Just give me a second, I'll open that. Okay, just look at this. So here we are given kernel function. Okay, put the vectors in the kernel function, get the value. After that, whatever the value you get using the kernel function, try to split that into two vectors and two vectors of the same form. By that, what I mean here, the first component is what? F1 square. Here you have G1 square. Here you have F2 square. Here you have G2 square. Here you have 1. Here you have 1. Here you have root of F1, F1 Y1. Sorry, F1 F2, and here you have root of G1 G2. Here you have root 2 of, sorry, my bad, I think I said something wrong. This right here is root 2 F1 Y1. This here right here is root 2 G1 G2. This right here is root 2 F1. This right here is root 2 G1, and this right here is root 2 F2, and this last component is root 2 G2. So they are in same form, right? So whatever value you get using the kernel function, try to split that into two vectors of same form. So if you split it, you get the mapping. So this is the original vector and we are mapping it to this. This right here is your mapping. So we have to do this here. Okay, let's try. Okay. So kernel function is x transpose y whole square of this plus 1. Okay, and now what, let's say x is, okay, what is the dimension? Okay, it is R2. x1, x2, y1, y2, square of this plus 1. Now take the dot product. So this is what x1 y1 plus x2 y2. Okay, square of this plus 1. Now use a plus b whole square formula. So this is x1 square y1 square x2 square y2 square plus 2 into x1 x2 y1 y2 plus 1. Okay, so this can, if you look at each term, you can split each term into two factors, and one factor will be entirely made of x components, and one term will be entirely made of y components. Okay, and wherever you have constant, you can simply take root of that. So this is equal to, let's make the vectors. So 1 2 3 4 4 terms. 1 2 3 4. So x1 square, x2 square. Wait a second. Yes, correct. x2 square. Then here you will split it into root 2 x1 x2, and the last term is simply 1. And the other vector will be y1 square, y2 square, root 2 y1 y2, and the last term is 1. Okay, this right here we have vectors. So now you know the mapping. So we mapped this to this right here. So let's write it formally. So phi of x1 x2 is equal to x1 square x2 square root 2 x1 x2 1. Is this clear to you all? Hello?
Yes, sir.
Yes, sir.
Clear.
Okay, good. Yes, this is, these few questions are very important. They do come in exam. I mean, obviously all of them are PYQs, but these are frequent ones. Okay, let's move to the next question. So here also we have to check if the function given is valid kernel or not. Yes, so do you guys want to try this? Yes, no.
Yes, sir. We'll try.
Okay, let's try to do this without using pen. Okay. Okay, so let's look at the first function k1. The first term, this you can split into x1 y1. The second term you can split into x2 y2. The third term you can split into x1 x2 and y1 y2. So first one is good, correct? Are you able to see the vectors from it coming from it?
Yes, sir.
Okay. Now speaking of the second one, okay, this right here you can also split. Everything is same, but the last term will be 1. So root of 1 is 1.
Yes, sir.
Correct?
Yeah.
Are you able to see it? So both are valid, right?
Yeah, both are valid.
Okay, good. Yes, thanks for bringing that idea that each term must be able to we can factorize each term and check. Okay, thanks. Now let's move to the next question. Okay, in this question, the kernel K is from R2 to R. Okay, that's always the case. From RD to you move to R. Okay, and the polynomial kernel of degree 4 we are given. And we are given vectors and we have to apply kernel function on them. So here directly they are giving that you are using polynomial kernel of degree 4. So what is the formula for polynomial kernel? Do you guys remember? Hello.
It will be x1 into x2 plus constant square.
X transpose Y. Uh, this raised to the power P plus 1. Do we have, or do we have plus 1 inside? Okay, I got confused. Let us see. What's the formula? Okay. Yes, right here. Okay, 1 is inside. Okay. Second. Okay. So the 1 is inside. X transpose Y plus 1 whole raised to the power P. And P is the degree. Okay, so here degree is 4. So plus, so the dot product is what? This is 2. 2 minus 1, this is 1. So this is, okay, I'll write it. So 2, 1 into 2 minus 1 into 1. And plus 1, and this whole raised to the power 4. So this right here is 2. 2 minus 1 is what? It is 1, and plus 1. So this is 2. 2 raised to the power 4. So this is equal to what? 16. So is this clear to you all?
So shouldn't it be minus 1? 1 into 2 minus
Oh,
minus 1 into 1.
okay, is that? I mean, let me check
I
that
think
again.
this is correct.
Let me check. Let's check the formula once again.
असाइनमेंट मिल गया मुझे
Yeah, this is plus. This is plus 1. This is correct.
वो तो तुम सुबह से बोल रहे थे कंफर्मेशन मिल गया
So let's move.
यहाँ पे पूरा वो हो गया है, यहाँ पे सिर्फ नहीं होता।
Yeah, someone's mic is on. So could you guys check? Okay, thanks. Great. Okay, let's move to the next question. In the next question, we are given, consider a data set consisting of 1,000 samples in a 20-dimensional space. You apply kernel PCA with polynomial kernel of degree 3, okay, to reduce dimensionality of the data. Which of the following statement regarding kernel PCA is true? Kernel PCA always returns, kernel PCA always results in a lower dimensional representation of data compared to standard PCA. So is this true? Is this always true? Few moments ago we discussed that what happens in kernel PCA. You have, let's say, data in R2, you transform it to R6 to capture the relationship and then reduce it to R3. So not always you are doing dimensionality reduction compared to the original data set, correct? So is this option correct or not?
That's wrong.
Correct. I mean it is wrong. So the second option is kernel PCA can only be applied to data set that are linearly separable. No, this is not true, right? This is not true. The reason why we apply kernel PCA is to capture non-linear relationship, right?
Yes. So second statement is also false.
Let's talk about the third one. Choosing a higher degree polynomial kernel. In kernel, PC can lead to, okay, what is this? Okay, I haven't heard of this term. Okay,
To
let's
increase.
Google up. Okay, let's Google about this term. Okay, let me Google the meaning of this term first of all. Hmm. To increased flexibility. Is it typo?
Yeah, it's a typo. It's typo, I think.
Yes, it's typo. Okay, so to increase the capture, yes, this is right. You increase the flexibility to in capturing nonlinear relationship, right?
Yes.
Uh,
Yes.
so this one is correct. This is typo here. Okay, now let's move to the next question. So suppose that we have a data set, data matrix, and this X belongs to R D cross N, where D denotes the number of features and N denotes the number of samples. Okay. Assume that D is very large compared to N and the data is centered. Okay. The representative line is given by the unit vector. Okay, pointing in the direction of line is W. This vector is W. Okay, so in all cases, this is the objective function we want to maximize, right? We have already discussed this. And where C is your covariance matrix, and the kernel matrix is defined like this. Okay, so in this case, when D is very large compared to N, what we do, we do not use covariance matrix, right? We instead use X transpose X, correct? Find its eigenvectors, and from its eigenvector, we move to eigenvector of C. Is that clear? Do you guys remember that?
Yes,
Because
sir.
is why we do that, because computing the eigenvectors of covariance matrix is computationally heavy. Why? Because what is the dimension of this? This is D cross D, whereas this vector is N cross N. Finding eigenvectors of this is easier, right? So this is the setup, and now let's check the options. So the eigenvectors of C and K are related by a scaling factor R belonging to small r belonging to R. So this is true, right? Correct.
Yes, sir.
If I remember correctly, it was like beta 1 is equal to uh, alpha 1 by root.
Yes. Yes, sir.
Yes, root of lambda 1. Yes, you can check that in notes. Okay, the second option is computing eigenvector using the matrix K reduces the number of computations significantly than using matrix C. Yes, this is the reason why we are doing this. This is also correct. The third option is suppose the maximum eigenvalue of C is lambda 1, then the maximum eigenvalue of X transpose, X X into X transpose in is n times lambda 1. This is also true, right? Because the eigenvalue for this X transpose X, this is the covariance matrix, right? Or, okay, my bad, not this. 1 by n, X into X transpose. So for this, you have lambda 1. So now uh, the eigenvalue for X into X transpose will be n lambda 1. And we know that the non-zero eigenvalues of X into X transpose is same as non-zero eigenvalues of X transpose X. So X transpose X will have n lambda 1. This is the eigenvalue. So this is also correct. The eigenvectors of C belonging to R3, RD, and K belonging to RD. Okay, they're talking about eigenvectors. Yeah. So this is correct, right? because they are in same space, but they have difference of scaling factor. Correct? Is this clear? Yes, no.
So XX transpose will be n cross n, no?
They are talking about the eigenvectors, right? Okay, wait a second. Wait a second. Let me think about it for a second. Yes. Okay. So this will be, so C belongs to R d cross T, correct? So the eigenvectors for this, let's say, eigenvectors are W1. So this will belong to RD, correct? For K will belong to R n cross n. So is W for this, the eigenvector I'm saying, this will belong to R cross R n. Yes,
Yes.
this is correct. Yes, this right here is wrong because of this. This is wrong. Now the last option is the eigenvalues of both C and K are non-negative. Yes, that's true, right? Because
Yes. Symmetric.
X transpose X and X into X transpose, they are symmetric, right?
Yes, sir.
And the other reason is that what are eigenvalues actually? They are amount of variance captured by eigenvectors in their respective direction, right? And variance can't be negative, correct? That's the other reasoning you can give for this. So this is correct. So is this question clear to you all?
Yes, sir.
Okay, I want to verify one thing. Let's go and open notes of week 2. Okay, where do we have? Okay. Okay, yes, correct. Because okay, the this alpha is what? This alpha is the weights, right? We know that all W's are linear combination of uh sorry, all data points are linear combination of W's. Yes. Okay, correct. Yeah, that is correct. I mean that second last option is incorrect because yes. Okay, let's move ahead to the next question. Which of the following matrices helps in transforming eigenvectors of K to vectors of C? So is it X? Is it X transpose? Is it C minus 1, K
Yes.
minus
C
1?
inverse, I think. I think there's C inverse, K inverse, X inverse.
Yes, C inverse, K inverse, X inverse. Okay. So how do we calculate from the eigenvectors of W, sorry, from the eigenvectors of K, how do we go to eigenvectors of C? Let's look at that. We have done that already in week 2. Okay. So this right here is what? The eigenvector of K. Okay. From here we move to beta. Sorry, from here sorry, my bad. Okay, sorry. So these betas are what? These betas are eigenvectors of K. From the beta, you find the value of alpha. And what is alpha? Alpha is actually the weight vector. Correct? Is that clear? Hello.
Yes, sir.
Okay. And how do we get to eigenvectors of C? But one thing here is that we actually can't compute W's, right? I mean, by eigenvectors of C, we mean W's. Correct? So we can't find W's, and why is that? Because to get the W's, we must know the mapping, right? Okay, where is that? Okay, this. So we must know the mapping. Okay, where do I have that? But okay, yes. So after finding alpha, and alpha is what? Weight. We can find W's, but we must know the mapping, right? The mapping. But this defeats the whole purpose. So here we sacrifice one thing. Here we sacrificed finding the values of W's. Correct? Do you guys remember this?
Yes, sir.
Here we sacrificed finding the value of W's, and we thought, okay, we cannot find W's, but we can find the uh, data points in transformed coordinate system, right? Using this. So how do we? So the question we asked ourselves is that why do we need W's? We need W's to take dot product of a data point with W's, right? To get the uh, new data point in new coordinate system. So for this we have to do phi of xi transpose wk, and this can be this we can simplify, and what is wk? We can write wk in this form. So wk is nothing but uh, your linear combination of data points, correct? So from there we get this, and just simplify it and make this phi xi transpose phi xj transpose, and this right here is what your using the kernel function we get this value, right? And this value is nothing but the i the ij element in the matrix of k. Do you guys remember this? Hello?
Yes, sir. Yes, sir.
Yes. So from this, I mean, the main reason here why I came here is that we cannot find the values of w's. Okay, I mean, in my understanding, we cannot find the value. Okay, so which of the following matrices helps in transforming the eigenvector of k and eigenvectors of k to the eigenvectors of c? Okay, let me check the answer for this. Just a second. Correct answer is B or A, I guess. Okay, I'll get back to you guys on this, right? Is that okay? We can discuss this in Saturday session. Right at the moment, I'm not able to figure this out. Is that okay with you all? Hello, hello. Okay, yes. Please remind me of this. Okay, next session we'll have on Saturday, so we'll discuss it there. Yes, and in the last question, suppose that 95% of the variance of the data is captured by using d minus 1 eigenvectors. Okay, this implies what? Okay, feature are highly correlated, and the other thing is features have low correlation. What can you say? Okay,
Highly correlated.
and why is that?
Because if you consider them to be lowly correlated, then
Hmm?
we would be able to eliminate most of the features. Here we are carrying we need almost d minus 1 eigenvectors, which means they are closely related so that we can't reduce their dimensions.
Yes,
Yes,
correct.
sorry,
They
dimensions.
so
Yes.
correct, absolutely correct. Yeah. So is this clear to you all?
No, sir. I was thinking low correlation means more eigenvectors.
Yeah,
Can you?
even I was thinking the same.
Okay. Okay, so let's think of it. Okay. Okay, more when the features are uh, decorrelated, in that case, what will happen? So the eigenvector, so the first eigenvector, so features are decorrelated. So the eigenvectors will capture less variance if they are decorrelated. Each eigenvector will capture less variance. And why is that? Uh, because eigenvector is in a particular direction. Okay. So if the features are decorrelated, that direction will not capture variance for uh, a lot of features, right? Maybe if two are correlated, so it will capture variance for two, okay, that direction. So if they are not correlated, in that case, we need more directions to capture the entire variance,
Yes.
correct?
Yes.
Okay, so this means if they are decorrelated, we need more eigenvectors. And in this case, how many eigenvectors we need? We need d minus 1. So this means we have highly decorrelated
Yes, sir.
features.
Correlated is low correlation, no, sir?
Yes, yes. Yeah, so B is correct. Okay. Is the idea clear? Yeah, as somebody, yes, haven't seen the name, my bad. Yeah, so someone came up with the solution, right? Is this idea clear to you? Hello?
Sir, but then like suppose let's say like
Hmm?
yeah, you need to like find out the pricing of a house, let's say. And so first like you are given the space, like the area of the house, so this is one feature. And next one is going to be like number of rooms, this is going to be the second feature, right?
Yes, yes.
Okay,
Continue.
so in that, and let's take the third feature to be the number of trees that is nearby this house. And in order to predict the value of this house, so the third feature is not related, right? it's it is going to have very less relation to the price of the house, correct? Which means we can drop the third feature, like the number of trees that is nearby.
Okay, it is not related. You are saying
Yeah,
if
so
the so what are we doing here? We are not drop the idea of PC is not to drop the feature, right? So it finds the direction where you capture.
we are reducing the dimension, right? Like by removing the third one only, we are
Okay, okay. You
reducing.
are thinking it that way. Okay, let's think about it. What is PC doing? It is finding the direction in which you have most variance. First of all, PC1, and that direction will be what? It will be combination of few features, right?
Yes, sir.
Okay, so each direction represents combination of few features,
Okay.
some linear combination.
Yes, sir.
So that direction will capture the variance for those features, right?
Yes, sir.
Let's say a particular direction, PC1 is what? Uh, Height plus weight by root 2. So it is capturing for these two features, the variance, correct?
Yes, correct.
Why? Because these two are correlated. If let's say if some other feature is not correlated, that will not be captured by this direction, right? So to capture the variance in that, we'll need another direction,
Okay,
correct?
sir. Yes.
So the whole idea is that, okay, what is PC? What are PC1, PC2? They are doing. They are capturing direction in a particular direction. They are capturing variance in a particular direction. So when when the features are decorrelated. That means they are not dependent. Loosely say, we can say they are not dependent. It means we'll need more directions to find the total find variance. More the direction we need, more if features are decorrelated, we need more directions. Let's say if all the features are highly correlated, in that case we'll only need few directions to capture the variance, right?
Yes, sir.
Because let's say we have three features: height, weight, and let's say BMI. Okay, height,
Okay.
weight, BMI. If they are highly correlated,
Yeah,
this
like we
means
can, yeah,
a
we
single
can.
direction, can capture all the variance in them, or almost all the variance in them. And the
Yes, sir.
reason is that they are highly correlated.
Yes, correct.
So if the features are decorrelated, then you need more eigenvectors, then you need more PCs to capture the variance.
Yes, sir. Yeah, got it.
So is this clear to you
Got
all?
it. Yes,
Yes,
sir.
sir.
Yes, so this was the last question. We have left this second last question. Okay, we'll discuss this in next session. Okay, right now at the moment I'm not able to figure this out. Yes, Dilraj.
Sir, I have a question.
Yes.
Sir, I am not confident in MLT. I have taken the MLP course in this term, but I am not confident in MLT. Can you suggest me a path that I can gain confidence in the MLT?
So the best resource is lecture videos. There is nothing better than that. If it is
Okay,
possible for you to watch the lectures again, that's the best thing.
okay. Thank you, sir.
Just a second. Just a second. That was okay. Okay, so that's it for today's session, guys. Now, hope this was helpful to you guys. Okay, let's meet again on Saturday.
Sir, this recording is available, sir.
Okay, this is getting recorded at the moment. This will take few hours for processing, and after that we'll upload it on YouTube.
Okay, sir.
Yes, thanks for joining the session. I'll do one thing. I'll share the lecture notes in the chat, and it will be also added in description of YouTube video.
Okay, sir. Thank you, sir.
Thank you, sir.
Guys, one request from my side, please don't call me sir. I am not qualified enough.
Okay, Pandit.
Okay, I have shared notes in chat. Okay, once again, thanks for joining the session. We'll meet again on Saturday, hopefully.
Thank you.